Hello everyone. Welcome back to the Orbit Unknown. Today we'll discuss about very interesting topic, why can't stars grow forever? The ultimate size limit explained. Part 1. Look up at the sun for just a moment, and it is easy to assume you already understand it. It feels ordinary, dependable, the same fiery disk that has hung in our sky every single day of your life. Our sun is a fairly average star, not a shrimpy red dwarf, but nowhere near the biggest thing out there either. Still, next to our own planet, it is almost impossible to wrap your mind around. Its diameter is about 109 times wider than Earth, and it holds nearly all the mass in our entire solar system, somewhere around 99.86% of it. And yet, as massive as that sounds, the sun is not even close to being the largest star we know of. That title belongs to a very different kind of star, one so enormous that comparing it to our sun feels almost absurd. Its name is Betelgeuse, and its diameter stretches out to roughly 1.4 billion kilometers. For perspective, our own sun measures about 1.4 million kilometers across. Do the math and you land on something staggering. Betelgeuse is approximately 1,000 times larger than the star that lights up our entire solar system. These are not numbers our brains were built to picture. You can say them out loud, you can write them down, but truly imagining a sphere that size is nearly impossible. So naturally, a question starts to form. Is this it? Is Betelgeuse as big as a star can possibly get? Before we can answer that, we need to understand how a star manages to grow into something this massive in the first place. The whole story begins with one of the most basic forces in the universe, gravity. Scattered throughout space are enormous, drifting clouds made of gas and dust, cold and quiet, and seemingly lifeless. Slowly, these clouds begin to collapse in on themselves, pulled together by their own gravity. As more material crowds into a smaller space, the pressure at the center climbs higher, and the temperature rises right along with it. Eventually, the core becomes so unbearably hot that something extraordinary ignites, a nuclear fire that will burn, in some cases, for billions of years. In that instant, a formless cloud transforms into something entirely new, a glowing, radiant star. Once that fire ignites, two enormous forces begin an endless tug of war. The nuclear fire in the core pushes outward with tremendous force, while gravity pulls just as hard in the opposite direction, trying to crush everything back down. As long as those two forces stay locked in balance, the star holds steady. Neither one wins. Neither one loses. This is exactly the situation our own sun has been living in for nearly 5 billion years, a calm equilibrium that has allowed life on Earth to exist in the first place. Betelgeuse, however, never had the luxury of a calm, drawn-out life. From the very beginning, it was already 15 to 20 times more massive than our sun, and mass changes everything about how a star behaves. There is a rule that governs almost every star in the universe. The more massive a star is, the faster it burns through its fuel. Picture two campfires side by side, one built from a small pile of branches, the other stacked high with an entire truckload of wood. The larger fire roars far brighter than the smaller one, but that intensity comes at a cost, burning through its fuel supply at a dramatically faster rate. Our sun still has an estimated 5 billion years of fuel left. Betelgeuse has already torn through nearly all of its fuel in just a few million years, a blink of an eye by cosmic standards. So what happens when a star like that finally starts running out of gas? Something strange, almost paradoxical, takes place. Deep in the core, the remaining material contracts and grows even hotter, squeezing tighter under gravity's pull. But the outer layers respond in the exact opposite way, beginning to expand, ballooning outward at an incredible rate. The delicate balance that had kept the star stable for millions of years finally breaks apart, and the outer layers are flung outward, farther and farther, until the entire star swells to many times its original size. It is a bit like watching a dying campfire flare up one last time before collapsing into embers, except on a scale involving an entire star. Betelgeuse is not some young star bursting with energy at its peak. It is old. It is dying. And what we are witnessing is the final, dramatic stretch mark of a star nearing the end of its story. The scale of that expansion is genuinely hard to comprehend. If you were to lift Betelgeuse out of its current location and drop it into the spot where our sun sits, its outer edge would reach all the way out to the orbit of Jupiter. Mercury would vanish inside it instantly. Venus would disappear. Earth would be swallowed whole, along with Mars right behind it. For planets, gone, consumed by the bloated outer layers of a single dying star. Betelgeuse is not massive because it represents some peak of stellar power. It is massive because it is unraveling, feeding on its own remaining fuel in one last desperate blaze before the end arrives. It is, in every sense, a sun staring down its own mortality, swollen, glowing, and counting down toward its final act. That final act is coming, and when it arrives, it will be unmistakable. Astronomers expect Betelgeuse to end its life in a colossal supernova sometime within the next 100,000 years, essentially tomorrow on a cosmic clock. When it happens, the explosion will burn so brightly that it will be visible from Earth even during daylight, shining for months with the intensity of a half-moon. It raises a fascinating question, though. If Betelgeuse only grew this enormous because it is dying, how large can a star get while it is still young and burning steadily rather than falling apart? Is there some kind of ceiling on stellar size? And if there is, what puts it there? Part 2. The answer takes us into the territory of some of the most extreme objects the universe has produced. And yes, there is a hard limit, and scientists gave it a name, the Eddington limit. To understand it, we return to the tug of war between outward pressure and inward gravity that keeps a star stable. The heavier a star gets, the hotter and brighter it burns, and at a certain point it becomes so blindingly bright that its own light starts pushing its outer layers away. That idea sounds like science fiction at first. Light pushing something away. Actually, light carries force, and this is not exaggeration. It travels through space as tiny packets of energy, and when those packets slam into a gas particle, they transfer momentum to it, not unlike one billiard ball clipping another and sending it rolling. Now imagine that on the scale of an entire star. An extremely massive star pumps out an incomprehensible number of these energy packets every second, and the combined force of all those impacts adds up to something enormous. Gas gets physically shoved outward, away from the star, and into the surrounding darkness. This is called radiation pressure, real enough that engineers have built spacecraft that use it for propulsion, so-called solar sails riding on sunlight. Around our sun, this pressure is far too weak to matter. Gravity wins easily. But around a star carrying hundreds of times more mass, the volume of light released becomes so extreme that radiation pressure overpowers gravity. Once a star crosses that threshold, it can no longer pull in new material, and anything trying to fall toward it gets blasted back out. The star ends up fighting itself, its own light stopping it from growing bigger. That is the Eddington limit, the point where a star becomes so brilliant that its brilliance puts a ceiling on how large it can become. So where does that ceiling sit? Current theory places it somewhere between 150 and 300 times the mass of our sun. Stars like that genuinely exist. One famous example, our 136A1, sits inside a small nearby galaxy, mass estimated between 200 and 300 times our sun, shining millions of times brighter. Set our sun beside our 136A1, and it would look like a match flame beside a raging bonfire. Stars at this scale are exceptionally rare and shockingly brief-lived. While our sun burns for billions of years, monsters like this tear through their fuel in a few million years, living fast and dying young. Could a star ever exist that breaks past the Eddington limit entirely? Almost certainly not. It could not hold itself together. The radiation pouring out would be so overwhelming that it would tear the outer layers apart before the star had a chance to form. What you would end up with is not really a star, but a runaway explosion that never settles down. There is one strange exception, coming from deep in the past. In the earliest moments after the Big Bang, conditions across the universe were radically different from today. Under those extreme conditions, the very first generation of stars may have formed, and some theories suggest a few could have been thousands of times more massive than our sun. We have never observed one directly, since they burned out long ago, but their theoretical existence hints the rules of the universe were not always identical to the ones we rely on now. Today, though, the boundary is firm. No star can hold together permanently past roughly 150 to 300 solar masses, and there is something almost poetic about that. The idea that a star's ultimate limit is baked into its own nature. At a certain point, it becomes the architect of its own destruction. But what happens when one of these colossal stars finally reaches the end? Because their deaths are every bit as extreme as their lives. An ordinary star like our Sun swells briefly into a red giant before settling into a small, dense leftover called a white dwarf, roughly the size of Earth, slowly cooling for eternity. Fairly unremarkable compared to what happens on the other end of the scale. For a galactic giant, there is no gentle winding down. When a star with hundreds of solar masses dies, it does not go quietly. Within seconds, the core collapses in on itself, and the outer layers come crashing down before being violently ejected back into space. The result is a supernova, an explosion so bright that for a short window it can outshine an entire galaxy, brighter than billions of stars combined. If it happened close to our solar system, it would appear brighter than the full moon. But for the most massive stars of all, the true titans, the destruction goes further. Their deaths trigger a rare, even more violent version of a supernova known as a hypernova. The energy unleashed is so staggering that it fires two narrow, concentrated beams of pure radiation into space, known as gamma-ray bursts, among the most energetic phenomena the universe has produced. A single burst can release more energy in seconds than our Sun will produce across its entire 10 billion-year lifetime. A number almost impossible to process. And what is left behind afterward, you can probably guess. For the most massive stars, there is no surface left, no remnant you could reach out and touch. Instead, the core collapses so